Hello everyone, we are Group 6.1 and today I will present the Chemistry Knowledge Map project, a unified knowledge graph that integrates chemistry concepts, occupations, skills, and educational resources to support personalized learning and career planning. This presentation covers 6 chapters: Introduction to the problem and objectives, literature review of existing resources and analytics methods, data science methods covering data sources and model design, result summary of the completed graph, discussions of key findings and conclusions with achievements, limitations, and future work. Chemistry information is scattered across databases using different formats and standards. Students cannot easily see connections between concepts, skills, and careers. Existing resources provide isolated information with no integrated view. So this project builds a chemistry knowledge map using knowledge graph and network analysis to link concepts, occupations, skills, and real-life applications into one connected framework. This project has 4 objectives: collect data from multiple public sources, clean and standardize it, construct a knowledge graph with semantic relationships, and develop a recommendation model for personalized learning. This scope covers 5 chemistry branches: physical, organic, inorganic, analytical, and biochemistry, using community detection, centrality analysis, shortest path analysis, and graph-based recommendation. KeyBuy provides a comprehensive chemical ontology with standardized identifiers, but focuses on biological relevance rather than education. ESCO classifies occupations and required competencies, but does not link them to chemistry knowledge. These 2 resources are complementary yet disconnected. Knowledge graphs and network X provide the technical foundation to bridge them. PageRank identifies foundational topics by evaluating incoming connection quality. Betweenness centrality measures how often a node lies on shortest path, reviewing bridge concepts between disciplines. The Louvain algorithm detects natural knowledge communities by maximizing modularity. For recommendation, we use TF-IDF vectorization and cosine similarity for content-based matching, with Streamlit and Pivot powering interactive visualizations. We integrated 4 public data sources. KeyBuy contributed chemistry terms, definitions, and ontology identifiers. PubChem supplied compound properties. ChemFount provided real-life and industrial applications. ESCO contributed chemistry occupations and job skills. The final dataset contains 98 chemistry terms, 47 compounds, 105 applications, 174 chemical application mappings, 59 occupations, and 1,229 skills. Key steps included text normalization, duplicate merging by entity type and name, and defensive handling of missing values and encoding errors. Categories were mapped to 5 standard disciplines. Since KeyBuy definitions were unsuitable for educational use, we replaced 35 physical and analytical chemistry concepts with textbook-level descriptions. Final validation checked file integrity and ensured every edge references existing nodes. The directed graph used 7 node types, and the construction proceeded in 7 stages from category nodes through chemistry topics, occupations, skills, applications, courses, and prerequisite links. The model takes a target occupation and existing skill, then outputs matched skills, missing competencies, recommended topics, courses, and a weekly study plan. Topics are ranked by a 7-factor score: name matching, semantic similarity, job relevance, category alignment, page rank importance, community membership, and industry demand. The innovation is combining graph analytics, centrality, community structure, prerequisite ordering with career-oriented prediction, not just entity display. The completed graph has 1,511 nodes and 5,189 semantic relationships. Skill nodes account for the largest proportion because occupations link to extensive ESCO competency requirements. Required skill is the dominant edge type. reflecting how chemistry careers connect to professional skills. The dashboard displays topics across physical, organic, inorganic, analytical, and biochemistry, conforming broad disciplinary coverage. Users can zoom, drag, and inspect nodes in the interactive graph. 3 exploration modes are available. The full graph supports filtering by category and entity type. The Category Explorer organizes knowledge by the 5 disciplines with definitions and applications. The Custom Explorer builds subgraphs from natural language queries with relevance scoring. The dashboard provides a complete dataset overview. In the environmental engineer example, the system detected only 2% skill coverage and identified major gaps in environmental legislation, recommendation techniques, and data analysis. It recommended chemistry topics, thermodynamics, chromatography, catalyst, and calorimetry, plus university courses and a 6-week study plan. This shows how graph relationships connect occupations and to required skills and relevant knowledge, making recommendations targeted and practical. A Year 3 student with chemistry lab skills compared ICT test analysis and agricultural scientist. Study duration was similar, but recommended topics and ROI scores differed. ICT offers strong analytical ROI, while agricultural had closer chemistry alignment. The system also suggests related careers and transition skills. By sharing skills and concepts through graph relationships, users can identify common competencies, estimate efforts, and explore alternatives flexibly. PageRank reviews foundational chemistry topics. Between its centrality highlights bridge concepts connecting disciplines. The vein partitions the graph into coherent knowledge communities. The industry analytics model summarizes skill demand. The practice quiz generates assessments by category or topic, and the job browser links occupations to required skills and chemistry topics for transparent career discovery. So we built a chemistry knowledge map integrating concepts, occupation, skills, courses, exams, and applications. The system goes beyond visualization by combining semantic matching, graph traversal, centrality analysis, community detection, and career recommendation. Users can explore, identify important concepts, discover related occupations, analyze skill gaps, and generate customized learning pathways, making the graph a practical decision support tool. So there are 3 main limitations exist. First, relying on 4 data sources means some concepts and occupations remain weakly connected. Second, TF-IDF-based matching cannot fully capture deeper semantic meaning. Third, English-only data limits multilingual accessibility. So we address this by refining matching with stricter similarity thresholds and token-aware strategies, and enhancing question generation and graph visualization quality during evaluation. So that concludes our presentation. Thanks for listening.